All right, let's dive right in. For thousands of years, one of the biggest questions you could ask was, what is everything really made of? Today, we're going to trace the incredible story of how a simple philosophical guess became one of the most important facts in all of science. I mean, just listen to the great physicist Richard Feynman. He believed that the single most important piece of knowledge humanity has is that everything is made of atoms. Think about that for a second. Not E equals mc squared, not the theory of evolution, but the simple fact that our world is built from these tiny, fundamental bits. It's the bedrock of pretty much everything we know. But here's the thing. For most of human history, this foundational idea was just that, an idea. It was fiercely debated, sure, but it was totally impossible to prove. So how did we get from a 2,500-year-old philosophical hunch to a scientific certainty? Well, that's the detective story we're going to unravel today. Our story doesn't kick off in some high-tech lab. Nope, we're going way, way back to the minds of ancient Greek philosophers. They didn't have particle accelerators or fancy microscopes. All they had was logic, reason, and a whole lot of curiosity. So on one side, you had this guy Democritus, and his argument was pretty simple. If you keep cutting something in half over and over, you've got to eventually reach a point where you just can't cut it anymore. He called that final uncuttable particle atomos, which literally means indivisible. But on the other side was Aristotle, who was, a pretty big deal. He argued that matter was continuous, that you could just keep dividing it forever. And because Aristotle was, Aristotle, his idea went out, and the whole concept of the atom got pushed aside for almost 2,000 years. The atom wouldn't really make its big comeback until the scientific revolution. And this time, the key that unlocked the whole mystery wasn't philosophy, it was chemistry. Scientists were starting to notice these really strange, really precise patterns in the way different materials would combine. Then, in 1808, an English chemist named John Dalton stumbles onto the first huge clue. He noticed that chemicals always combine in these clean, fixed proportions. Like how water is always 2 parts hydrogen to 1 part oxygen. The only way this made any sense, he figured, was if everything was made of discrete little particles, atoms, that were hooking up in simple, predictable ways. And just like that, the atom wasn't just a philosophical idea anymore. It was a real scientific theory you could actually test. This was a game changer. And once the floodgates were open, man, the evidence just started piling up. Just a year after Dalton, Gay-Lussac found that gases do the same thing with their volumes. Then Avogadro connects all the dots, proposing that this all works because equal volumes of gas have the same number of particles. The case for atoms was getting incredibly strong, even though no one had ever come close to actually seeing one. So, just as the scientific world was finally getting comfortable with the idea of a solid, indivisible atom, bam, a discovery is made that turns everything completely on its head. It turns out the atom wasn't so atomos, or indivisible, after all. A physicist named J.J. Thomson was experimenting with cathode rays, basically beams of electricity in a vacuum tube, and he found a particle that was almost 2,000 times lighter than a hydrogen atom. This little particle, the electron, had a negative charge, and it seemed to be a piece of all matter. The unbreakable atom had just been broken. So how do you even picture this new reality? Thomson came up with what's famously called the plum pudding model. Just imagine the atom is like a big, fluffy, positively charged dessert, and stuck inside are these tiny negative electrons, kind of like raisins. It was our first real attempt to draw a map of the inside of an atom. Now, this model made a very specific prediction. If you shot tiny particles at it, they should just sail right through the pudding without any trouble. But one of Thomson's own students, a guy named Ernest Rutherford, decided he was going to test that. And what he found was, it was completely shocking. Rutherford fired these tiny positive things called alpha particles at a super thin sheet of gold foil. And just like the plum pudding model predicted, most of them went straight through. But, and this is the crazy part, about 1 in every 8,000 of them bounced right back. Rutherford himself said it was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. It just shouldn't have been possible. There was really only one way to explain this insane result. The positive charge of the atom wasn't spread out like a pudding at all. Instead, it had to be concentrated in an unbelievably tiny, dense, solid core at the center, the nucleus. With the electrons orbiting way out in the distance, the atom wasn't a pudding, it was a miniature solar system. But of course, there's another plot twist. This new solar system model had its own fatal flaw. According to the classical physics of the day, an orbiting electron should constantly be losing energy. It should spiral into the nucleus in less than a second. Basically, all atoms should just instantly collapse. Since, we're all still here, something was deeply, fundamentally wrong with the laws of physics. The rules of the game had to change. So, in steps the Danish physicist Niels Bohr, and he proposes something truly radical. He suggested that electrons can't just orbit anywhere they want. They are restricted to very specific, stable energy levels or shells. They can exist in one shell or another shell, but they can never, ever exist in the space in between. And this is where things get really, really weird. To move between these fixed shells, an electron performs a quantum leap. It absorbs a precise amount of energy, and then it literally vanishes from its orbit and instantly reappears in a higher one. It doesn't travel between them. It's just gone, and then it's there. Then, when it falls back down, it spits out that exact same amount of energy as a tiny particle of light. And this wasn't just some wild guess he came up with. It perfectly explained a mystery that had stumped scientists for a century: why every single element, when you heat it up, emits light in its own unique pattern of specific colors. Those colors, they're like the atomic fingerprints, the precise energies of light given off as electrons leap between their own unique set of allowed energy levels. Even Feynman, who understood this stuff better than just about anyone, was still completely in awe of the fundamental constant that governs this whole quantum dance. He called it a magic number, a deep mystery that just seems to be woven into the fabric of reality itself. But the story doesn't end with Bohr's model. As our understanding got deeper and our tools got better, the picture of the atom became even stranger, and our ability to prove it was real became way more direct. So today, we know that even Bohr's neat orbits weren't the whole picture. Electrons don't actually follow these clean paths at all. Instead, they exist in these fuzzy, three-dimensional clouds of probability. We can never know exactly where an electron is, only the region where it's most likely to be found. The atom isn't a tiny solar system. It's a bizarre quantum cloud. And after this long, winding 2,500-year journey, that original question, are atoms real, was finally answered with a resounding yes. With amazing technologies like the scanning tunneling microscope, we can now create actual images of individual atoms. We can even nudge them around one by one. The debate is over. So we've gone from the idea of an indivisible little ball to a divisible cloud of probability. We solved one ancient mystery, only to discover a dozen new ones that are stranger than anyone could have ever imagined. The atom is real, but reality itself is far, far weirder than it looks. It really makes you wonder, what other unbelievable mysteries are just waiting for us down there in the quantum realm?